Welcome back to The Explainer. Today, we're taking on a subject that challenges the absolute very foundation of our daily existence. We're talking about the mind-bending reality of our four-dimensional universe. So if you think you have a pretty good grip on how time passes or how space surrounds you, well, prepare to have those assumptions completely upended. We're going to pull back the curtain on reality today to see the invisible geometry that governs literally everything, from the screen you're looking at right now all the way to the farthest edges of the cosmos.
Think about this for a second. What if your past is actually someone else's future? I know, it's a completely bizarre question. I mean, every single day we experience time as a constant, right? It just ticks forward at the exact same pace for everyone everywhere. We base our entire lives around this shared assumption that a second for me is exactly a second for you. But when we start looking at the physics of extreme conditions, that shared universal clock just completely shatters. In certain scenarios, observers actually can't even agree on the sequence of basic events. And that leads us to the profound, slightly unsettling realization that my past could literally be your future.
To understand how that is even remotely possible, we kind of have to rethink reality itself. Enter spacetime. Basically, it's a mathematical model that fuses the three dimensions of space, length, width, and height, with the one dimension of time. For centuries, we treated these things as totally distinct. We thought space was the box, and time was just the clock ticking away outside of it. But they actually aren't separate at all. They are inextricably woven into a single four-dimensional fabric. So a point in space isn't just a place anymore, it's an event. It requires four distinct coordinates to define exactly where and, crucially, when it happened.
Now this really perfectly illustrates the paradigm shift we're talking about. In classical physics, think Sir Isaac Newton here, space is just a rigid 3D stage. And time is just an independent, invisible clock ticking universally in the background for all the actors on that stage. But then we get the relativistic view, championed by Albert Einstein and Hermann Minkowski, which completely fuses them. Suddenly that rigid stage becomes flexible. The actual rate at which time passes for an object depends entirely on its velocity relative to whoever is watching. So speed physically alters time.
Okay, let's get into the mechanics of this in Section 1. Speed, space, and pancakes. Stick with me here.
Imagine you're standing still on the sidewalk and you're peering at the wristwatch of someone who is just zooming past you at near the speed of light. From your perspective, looking at them, their watch would appear to be ticking incredibly slowly. In fact, if they moved fast enough, their time would seem almost totally frozen. This is what we call time dilation. But here's the real kicker. Motion is relative. So from their speeding perspective inside that ship, they feel like they are stationary, and you are the one moving backward past them at near light speed. So to them, your time seems to be moving in fast forward. Everybody thinks the other person's clock is broken.
And time isn't the only thing that gets messed with here. If you looked at that same fast-moving person from a profile view, they would appear physically squashed flat, literally like a pancake in the direction they're traveling. This bizarre effect is known as length contraction. Now, to be clear, they'd be completely unharmed, and if you viewed them head-on, they look totally normal. But at extreme speeds, space itself contracts. The actual physical distance they occupy shrinks from the perspective of an outside observer.
Let's actually attach some real numbers to this to make it concrete. Imagine an Earth to Mars space race. We've got Terrence, our stationary official sitting on Earth, and we've got Stella, who is in a ship traveling at half the speed of light, so 0.5 c. Terrence observes Stella crossing the finish line and clocks it at exactly 600 seconds. But Stella, who is actively experiencing time dilation, checks her ship's chronometer and sees that only 519.62 seconds have passed. She also calculates the actual distance to Mars as being significantly shorter than Terrence does. They fundamentally, mathematically cannot agree on the time or the distance. The math works out perfectly for both of them, yet their real, lived realities completely disagree.
So what does it actually feel like to be Stella in this scenario? Well, if you are inside that speeding rocket, you never actually notice these bizarre effects. To you, your watch ticks normally. You look completely normal in the mirror. Your personal experience of time, what physicists call your proper time, and your perception of your own size, your proper length, they never change within your own frame of reference. It is wild to wrap your head around, but everyone is perfectly correct about what is happening in their own frame. Your reality is entirely bound to your speed.
Moving right along, let's hit Section 2, Mapping the Light Cone.
Okay, try to visualize this. Think of an event in space-time as a series of photographs. Each photo is a single, frozen moment. Now, instead of lining them up chronologically from left to right like a timeline, imagine stacking them flat, one on top of the other. If these pictures were printed on clear plastic sheets, we could look from the bottom of the pile all the way to the top to see events evolve over time. When Terrence and Stella disagree on when and where things happen, it's essentially because their different relative speeds cause them to view this stack of clear pictures from entirely different angles. They're slicing through the exact same four-dimensional block of reality, but they're doing it at a slant.
Now you might be wondering, if everyone is looking at a different angle, how does logic even survive? Enter Roger Penrose's famous light cone. While Terrence and Stella are definitely going to disagree on specific times and lengths, they will always agree on the space-time interval between two events. Think of it as a universal translator. This cone beautifully visualizes causality, because even with time dilation, we can never, ever witness causally connected events in the wrong order. It doesn't matter how fast you are moving, there is no scenario where you could see a light bulb illuminate before its switch is flipped. The boundaries of this cone dictate the absolute, hard limits of cause and effect in our universe. This mathematical realization fundamentally changed physics forever. Back in 1908, mathematician Hermann Minkowski, who was actually one of Einstein's former professors, delivered this massive, historic realization. He said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." By recasting space-time as a purely geometrical idea, he gave this intense, almost philosophical mic-drop weight to what was previously just really complex algebra. It meant the universe was fundamentally, at its core, different than human intuition suggested.
And if you push this geometry to its ultimate extreme limit, you get something incredible. Look at photons, particles of light, traveling along the outer edges, what we call the null cones. Because light travels at the absolute maximum speed limit of the universe, a photon doesn't actually experience the passage of time at all. Seriously, let that sink in for a second. To a photon, there is absolutely zero elapse of time from the moment it's created inside a distant star to the moment it hits your eye billions of years later. Time simply does not exist for a particle moving at the speed of light. Its birth and its absorption happen in the exact same instant for it.
All right, let's bring these massive cosmic concepts back down to Earth. Section 3. Space-time in everyday life.
Because space-time is a literal fabric, it can be warped and stretched. General relativity proves that massive objects actually curve space-time, and then other objects respond to that curve. This creates phenomena like gravitational lensing. Basically, when light bends around a supermassive object, like a black hole, that object acts like a giant cosmic magnifying glass. The light travels along the curved space-time fabric, dipping and bending with the geometry. And this actually allows astronomers to see entire distant galaxies that are hiding millions of miles directly behind the black hole.
And look, these aren't just fun, hypothetical cosmic thought experiments. They impact your reality right now, today. First, light always travels at the exact same speed for all observers. It is the literal universal speed limit of causality that holds our shared reality together. Second, even the Earth's rotation physically twists and distorts the space-time fabric around us, right where you are sitting right now. And finally, if you use the map app on your phone today to get somewhere, you relied on this exact math. Your GPS has to constantly calculate and correct for time dilation between the orbiting satellites and your phone on the ground. Without Einstein and Minkowski's 4D continuum, your GPS would completely fail and send you miles off course in a matter of minutes.
So we've seen how speed warps length, how movement actually slows down time, and how it is all perfectly connected in a single geometric continuum. As we wrap up this explainer, I want to leave you with one final thought to chew on. Where are you in the four-dimensional fabric of the universe? Every single step you take, every time you hit the gas pedal in your car, you are altering your unique, personal trajectory through space-time. You are subtly changing your own personal clock relative to the rest of the cosmos. Keep pondering that the next time you check your watch. Thanks for joining us, and we'll see you next time.